Number 34. Number 34 is similar to number 33. We have the integral from 2 to 4 of 1 over x minus 3 squared. Okay, so very similar, and when we look at the graph of this, the graph looks fairly similar to the previous example. Okay, it's a little bit different in that it's a little bit further away from that asymptote. Okay, so the same thing still applies here in that when we look at the picture of this, from 2 to 4, we're going to integrate across a vertical asymptote. We cannot integrate across vertical asymptotes. We have to break those into left side of the asymptote, right side of the asymptote. And because we're integrating using an asymptote as a bound, we're going to use a limit to do this formally. So then the left-hand integral is going to be that yellow area. So the yellow integral goes with the yellow area. The green integral goes with the green area. And I'm just going to now anti-differentiate this. So when I anti-differentiate this, I'm going to end up with negative, or I need to use a limit because I'm going to still use a. So limit as a approaches 3 from the negative side. The antiderivative of this is going to be negative 1 over x minus 3 to the negative 1. So the negative puts it in the denominator. And I end up with a bound of 2 to a. So I use my power rule. The power is negative 2, so it goes to negative 1. I account for that negative 1 power with that negative 1 in the numerator. And then I increase the that power negative 1, I just leave it in the denominator like that. Plus, again, for this side here, we're going to end up with the exact same integral because it's the exact same expression. But I'm going to write this as a limit going to 3 from the positive side in this case. And I'm going to have different bounds, but the integral will still be the same. It'll be negative 1 over x minus 3 to the power 1. My bounds are going to be from a to 4 or 3 to 4, basically. So working out the value of this integral, I'm going to plug a equals 3 in. So I'm approaching 3 from the negative side. So for example, it's going to be 2.9. So what is going to end up happening is I'm going to end up with a negative 0 in the denominator. So basically it looks like this. Since I'm approaching 3 from the negative side, I'm going to end up with a negative 0. Okay, and that works out to be 1 divided by 0 is infinity. 1 divided by negative 0 is negative infinity. So we have a double negative, so I'm going to have an infinite area here. And it's going to be minus negative 1 over 2 minus 3 is negative 1. So it's going to be minus 1 on this side. Okay, so that's still infinity though. On the right-hand side, I'm going to work out this. I'm going to plug 4 into this integral. So I'm going to end up with negative 1 over 4 minus 3 is 1. Minus, I have negative 1. This time I'm approaching 3 from the positive side. So I'm going to end up with 0 from the positive side. And that's going to be positive infinity. So I'm going to end up with negative 1 minus a negative is positive, and then I'm going to end up with positive infinity. So it's going to look like that. So the unbounded area to the left is infinite. The unbounded area to the right is also infinite because we should kind of expect that because that is symmetrical. So the net area is going to be infinite. So the answer in this case, the area to this is going to be none of these. And this is a difference between this graph and the previous example of x minus 3 to the power 2/3. The power 2/3 is a power less than 1. That means that the area bounded by the asymptote is going to be finite. So if we were to go the other way to x equals infinity, that is an unbounded area that's infinite. So this area actually is infinite. Okay, this is finite. If we take a look at the power 2, well, the power 2 is bigger than 1. So what ends up happening is this area bounded by the vertical asymptote is infinite. And then this area down in here is finite. Okay, it just kind of switches. It just happens to be the case. This becomes very useful when we start getting into series in the second part of calculus.